All right. So lab schedule, again, there's only 2 labs. There's this lab 9 and 10 this week and next week. And then after that, the lab time is meant to be just time for you to work on this final project and wrap that up in the last, I think, 2 weeks of the class. Also, this is kind of the month of holidays. So don't forget that Tuesday is November 11th, Veterans Day. So there's no class on Tuesday. And then, Thanksgiving's not that far behind. So not a lot of classes this month, and then we'll be very quickly in the final. So the final project, that's the next deliverables here are the presentation video and the final report due the Wednesday of the last week of regular scheduled classes before finals week. So I'm working on getting you your feedback back on those input modeling reports, but just keep on plugging on your work on building your model and then analyzing your model to put that together. Just as a reminder, the idea is you have a 10-minute or less. There's nobody complains about a short video, so 10-minute or less video presenting your system, the general problem you're trying to solve, your methodology, so your simulation model at a high level, the results from your sim, and the conclusions you draw from those results, as if you're presenting them to a stakeholder who might be interested in making changes to that system. And so you upload that, and then you have this 4-page report. There can be extra pages like in the appendix if you need them. So again, you distill down the most important things that someone should take away and everything they need to basically follow those results. And then if you need the extra details of your model that are there to sort of help answer questions that someone might have that are down in the weeds, then you can put those in an appendix, which would be kind of unlimited. But the main bulk thing that you're graded on would be the 4 pages of this report. So not a long report, not hopefully a long video, uploaded the Wednesday of the last week of classes so that there's time for then you to get assigned one of those. Each individual one of you is get assigned one presentation video from another group and one final report from another group, so that you'll have a couple of days to watch that video, read that report, and fill out a little rubric and make some comments, and then you'll get your peer review credit for that. So that is, that's the schedule kind of going forward. Otherwise, there's ICAs, there's this homework that's out, and then again, I've said this a couple of times, the final homework, J2, it should be available now. And it's due the weekend before Thanksgiving. It's the final homework assignment. It's arena-based. And because we capture these metrics on it, then there won't be a solution set and it can't be dropped. So it will sort of be a homework that pulls together lecture and lab stuff and kind of, has you do a design problem. I give you sort of a model. You can modify the model. You do a little analysis on the model, and then we see how well things come together. So any questions? Okay. All right. So let's just do one of these. Just every once in a while, it's nice to do an early one. So I'll come back. iClicker. Okay. So question here is t-test, which we've talked a lot about. It is a location test. Assuming that the data are normally distributed, it evaluates the probability of a location, in particular the mean. So it's making an inference on a location, it's making an inference on a parameter. So because it evaluates the plausibility of parameters and not the distribution, so we take the distributions for granted, then what type of statistical test do we call a t-test? I'm looking for a 1-word or maybe 2-word answer. So just, these are just some terms that I want you to know so that later on in life, you'll know to search for these terms. When you're like, said, wow, I would like something like a t-test, but it's not appropriate for my data. So I need to search for something, a different form of test that's like a t-test. And so this is the form that we call the t-test. So what type of statistical test is a t-test? Because it makes an inference on a parameter. That's the hint. So go ahead and do that. I'll leave that. I'll leave that up for maybe a minute or so, while then we kind of plow on forward. So I'll leave the question up there. And I'm actually just looking for a one-word answer for this. And it's not one sample, it's not two sample, it's not one-sided, it's not two-sided. Hint is parameter. Okay. All right, so I'll go ahead and maybe with that up, I'm going to go ahead and close that clicker. So 5, 4, 3, 2, 1, and we're done. All right, so what I was looking for is parametric. So, that if you've got a test that makes assumptions on distributions and then tries to figure out the plausibility of certain parameters, it's a parametric test. And so, you can go, you eventually over your career, you build this kind of statistical decision tree in your head of tests. What tests can I use and when? And you can find people summarize these. I forget where I looked, but I went to some Wikipedia page expecting to see them do them. They summarize their tree as a table. And you can see this table says parametric and non-parametric location tests. And so then, in this table up here, it has a way, like a coarse-grained category here, one group versus two groups. That's basically like one sample versus two sample. And then it breaks down, are your samples independent or paired? And then so from there, do you have more than 30 or less than 30? And then from there, are they normally distributed or not? And then from there, you finally get okay, so if I have two groups that are independent from each other, there's less than 30, they're normally distributed, I land on the t-test. But if they weren't normally distributed, then I get a U-test or a Mann-Whitney U, which is the closely related Wilcoxon rank sum. Both of those can be used for that. And so, this just gives you a way to kind of cut through here. And I'm not going to do all of these combinations. You can see it down here under nominal measures. That's where the chi-squared test comes up. And so you see here where it's like, if I have, two groups, I want to test to see they're independent. I've got the average number in each bin is greater than or equal to 5. I do a chi-squared test. If it's less than 5, they suggest a Fisher's exact test. So there's this decision tree where, again, when you start this out, when I was in your shoes and first learning this stuff, it just seemed like all of these tests were just like over the top. It was like gratuitous. It just seemed like, why do we have all these different tests? Can't I just use one of them? Don't they all do the same thing? And they do the same thing, but they navigate that ROC curve differently. And so you get different amounts of power out of them. And so you want to use the highest powered test you can, because then you can make inferences with the fewest number of samples. But in order to use higher powered tests, you generally need to make assumptions about your data. And that's basically what comes out of here, the assumptions and constraints that are out of your data. So every test that's out, there's no redundant statistical test. They all have a purpose. They all have been marketed for a particular reason, a niche. And over time, you'll be able to start seeing those niches. And so now when I sit on comprehensive exam committees for PhD students, then they have to choose one of these. And so then we can stand back and we say, wait, are you sure you can use that test because of X, Y, and Z? Why didn't you use this other test? Why didn't you use this other approach? And because if you use the wrong test, then you can make an inference that just isn't justified at all from the data. So it is important eventually to build up a vocabulary of these tests. We're starting small, where we're just talking about things like t-test, the chi-square test, the KS test. So but I want you to at least see that there's a bigger world out there, and there is a map for navigating that world. And you will eventually learn that map if you keep doing this stuff. But so that's kind of that's what's on the horizon, and that's sort of where what we've been talking about so far. So now in this unit, we're going to take those ideas like the t-test, which seems like a pretty sort of boring, kind of esoteric, the academic thing that you wouldn't expect a stakeholder to understand. And how do we turn that into something a stakeholder would understand without having to teach them what a t-test is? And that is a big part of this lecture and the next lecture. so-called interval estimation. So every time you look at a confidence interval in election results, for example, and so on, you're looking at t-tests. Basically, there are some, there are some types of data that aren't fit for t-tests, but people want a confidence interval, so they build a confidence interval with one of those other tests that I just showed there. So, but the point is that every confidence interval is a summary of one of those statistical tests. And that's what we're getting into today. And I guess not Tuesday, because Tuesday's Veterans Day, but then Thursday. All right, so where do we start with that? Well, we need to know, what are we going to measure out of our sims? And then from measuring that out of the sims, how to summarize it. And then so from those summaries, how many replications are we going to need to use to generate these data? And then what additional measures do we have to put in to reduce bias? And so we stopped last time just introducing bias. It was in this context. So we talked about terminating and non-terminating systems. Terminating systems, we care about the whole system for when it starts to when it ends. So the start and end is a part of our operations. It's a part of our analysis, the terminating system. So if we're studying a terminating system, we build what's called a transient simulation. So we're not focused on just the steady state behavior. We're focused on all of the little blips and bips that show up in this data from the very beginning to the very end, a transient simulation. The other types of sim are these non-terminating sims, and that'll be the big focus of the next lecture, Thursday's lecture. So where here we're focusing on systems where when the system starts or when it ends is very rare. And most of the time we're just focusing on its steady state behavior. And so we need to build a simulation that doesn't model the whole life of the system. It models just the steady state behavior. So, and there will be different ways to make choices about the sims based on what we're simulating. And that's what we're going to start getting into today and then finish up with that next time. Now, when we look at a replication, so these things behind me, these are we're thinking of as per replication. Think about the sims you've done so far in labs. Every replication has a lot of data points that it generates by itself, but they are not independent data points. So customers at the beginning of your sim may have long wait times, and customers at the end of your sim may have short wait times, but customers around them are probably going to agree on wait times because their wait times are influenced by the state of the system. So the customers are correlated with each other. And that correlation across time, that's what we mean it's a violation of independence. And so we can't treat them like independent samples. Every customer is not a replication. Sometimes we call that a pseudo replication. You can't say like, oh, what was your experience today? And then you ask the next customer behind them and treat that as an independent replication. What you can do is say on today, for today, with the people staffing the restaurant today, what was the average happiness with how we were doing? And that average for that day, that is the single data point you use. The things you use to calculate that data point, those aren't data points. Those are just things you use to generate the data point because they aren't independent of each other. Data should be independent in order for us to get a snapshot. So we have a Monday and a Tuesday, and the Tuesday average happiness is hopefully independent from the Monday average happiness. So then when we average over the days, we get an idea of how happy things are. So that way, if we have, it might be that Monday was a really bad day, like a machine broke or something like that. And so people have really long wait times, but it's fixed by Tuesday. So Monday was an anomaly. So if we treated all the customers on Monday as independent samples of our system, we would bias our system because Monday was a weird day where one of the machines that we need to use is broken. So that's what we mean by it's important to have independence, an independent sample of these systems. And so within the rep, and so oftentimes when I use K or really this little n, I'm often going to use to say the number of, say, customers or data points within a replication. So within a replication, at the end of the replication, we can take an average, so this is with discrete time data. So each one of these is a customer, that's discrete, for example. And so we can say this is the average wait time for Monday, for the simulation of Monday. And we're rarely going to then think about confidence intervals or our standard errors or anything like that, because all of those things are correlated. So it kind of ruins all the assumptions for how we calculate intervals. But we just, let's say, so we have one data point. Monday's average was this, Tuesday's average was this, and so on. Alternatively, we can have metrics which are not discrete, that are defined over continuous time. So we could say, what is the current length of the line? At any instant of time, you could ask how long the line is. It isn't discrete. It's not like you say, oh, the line. I can't even come up with an example where it would make sense for that to be. Because here you can say, how long did the fifth passenger or the fifth customer wait, or the fifth passenger wait in an airport example. Here, there is no fifth. It's just what was the wait at a particular time? What was the wait an instant later, a wait an even smaller instant later, and so on. So for these continuous time data, we don't take an arithmetic average, a mean like this. We take this kind of generalization of an average to an integral. We take the integral underneath that curve, and then we divide it by the length of the interval. And that's what we refer to as a time average. You'll see that term in ARENA. Or time persistent data. That's something else that shows up in ARENA. So this, it still isn't, it's a similar interpretation. Like you could say on Monday, what was the average queue length? Well, that average queue length is under an integral. So you have the queue length at any instant of time. You take the integral under it, divide it by the length of the interval, and that gives you the average queue length for that day. So it's qualitatively different type of data than average wait time, which is over discrete elements. But at the end of the day, they're just still two numbers. So any questions about those two different, that idea of that you have discrete time data with an arithmetic mean, or continuous time data with the so-called time average or time persistent data? Okay. So, these are just some examples here. So discrete, on Monday, were we out of stock? At the end of the day, did we run out? So maybe on one day we did run out of stock, and on another day we didn't. So every day, that's discrete time, versus, like I said, the length of the queue. That's our continuous time example. So this length of the queue, I could be taking the average queue length, or I could just say, was my queue length longer than I want? And so in that case, I've kind of quantized the queue length, but it's still continuous time data. So I can still say, right now, is the queue length too long? And so the average of this thing, if it was 0, then that would mean our queue length was always within our performance desires. But if it's like 0.5, then that would mean that 50% of the time, the queue length is too long. 50% of the time, the queue length is greater than 10. That might mean that it's all at one time. It might be that it was less than 10 and then it was greater than 10 for the rest of the replication. Or that might mean that it's like a pulse width, it's like a pulsing thing where it's sometimes up, sometimes down, sometimes up, but then 50% of the time on average, it's above 10. So that would be, another metric we could take. Pretty clear? Those are points that we're going to take out of each replication. So from there, we have to say then, okay, those points. So so I've got this theta is here. I've got using theta for a discrete time average here. So I can say that there is a real average wait time in the real system. I'm estimating the average wait time in my simulated system. And I have to do that by running a certain number of replications of my simulated system. So I run a sim of Monday through Wednesday, and I have 5 average wait times. So then those 5 average wait times, I could take the expected value of them to get my predictor or my prediction of what the average wait time is for the real system. And that's this theta hat. So that is my my average across my simulation system. But if I ran a different 5 replications, I would get a different theta hat. And a different 5 replications, I'd get a different theta hat. And so I'm only going to run 5 replications. I'm not going to run 5 and then 5 and then 5 and then 5. The whole point of it is these are costly to run, so I don't want to run a lot of them. But when I'm building my system, I need to understand this idea of bias. And so what this idea of bias is it's saying that how much error do I have in my system, my systematic error. How much shift is there? So does my system consistently produce an average that is less than the real average in the real world? That's what this expected value is capturing here. So if you were to run your simulation, your experiment, your 5 replications 500 times, and then take the mean of those 500 experiments, then that would tell you the expected value across your experimental design. And if that thing is different than the real world one, then that we have introduced bias. And so it's often hard to measure the amount of bias in your system. I mean, it's like gerrymandering's in the news or whatever. And so we know that, gerrymandering introduces bias in voting, but it's hard to measure how much bias. But we know the process fundamentally, and we can study the process, and we know the process is a bias generating process. So likewise, it's going to be really hard for you to tell exactly how much bias your sim adds, but we know things in the sim generate bias. And so we can then work, and this will be primarily what we talk about Thursday, we can then work to eliminate bias by working on those processes in the system. And so this is like an abstract concept, this idea of bias. I'm not going to ever ask you to measure bias, but if we have a graph like this, hopefully you could spot it. So theoretically speaking, we could say, like, if you had a graph like this of your, these are, say, the wait times for customers as they enter the system versus when they exit the system. In a steady state system, we only care about these customers up here. These are just the customers that are warming our system up, because our system has to start somewhere, and it takes a while to get to steady state. And so we only care about these customers. And so in this cartoon example, it's very clear that the average we care about is the average of this population right here. And so that we want the average wait time to be kind of where I'm drawing this line, right here in the middle of these squiggles. But if I include this warm-up period, I'm going to bias the average down, and I'm going to get an estimated steady state that's less than usual. And if I always start my initial conditions less than the steady state, then that's going to tell me that, I'm probably always going to have an estimated wait time that's less than the real wait time. So we're going to talk about ways in which to try to reduce that on Thursday. But that's the idea of bias. I'm not going to have you calculate bias, but I want you to be able to recognize bias if you saw a plot like this, and understand what bias is and why it's bad. And so that you're motivated to know why we do things like come up with warm-up periods, which you're going to experiment with in the lab, and actually in that last homework. All right, any questions about the notion of bias? Okay. So the other point estimates that we're going to talk about are quantiles. Very often quantiles are actually kind of more interesting or more useful than means. And so, the idea behind a quantile here is you want to know, like somebody might ask you, what is the 85th percentile wait time? So what they're not asking for is the average wait time. They're saying, what is the wait time that is higher than 85% of all of the wait times experienced in the system? So this tells me that, the 100% wait time would be the maximum wait time anyone ever waits. But that's just too much. But the 85th% wait time tells me that, if I get this 85th% wait time, like if I can manage that, like the 85th percentile wait time is 5 minutes, then that means most of my customers wait 5 minutes or less. And so that becomes more interesting than the average wait time, where you say, well, the average wait time is 3 minutes. But that could mean that a lot of customers are way above average. And so the 85th percentile, so the 50th percentile is the median. So if I say, what is my 50th percentile? That is the wait time. That's the same thing as asking for the median wait time. So this is like, super median. It's like above the median. So it's saying 85% of the data are less than the 85th percentile. That's what we mean by a quantile here. So I've summarized that here mathematically. So if we say here that I have an output measure from my sim y, the P quantile, so it's like the 0.85 quantile or the 85th percentile, is the value theta such that the probability that the output from your system is less than or equal to theta is equal to P. So theta is the thing you're asking for. The thing you're requesting is P. So 85th percentile, that's the P, that's the 0.85. And then theta is the answer to that question. Equivalently, we can use a CDF for that. We can say the CDF that represents the distribution of our system. If you evaluate that at the answer to the question, it will be equal to the prompt from the question. So if you say, F of 3 minutes is equal to 85% or 0.85, then you're saying that 85% of the scores are less than theta. So this quantile, we've heard this word before. The inverse CDF is called the quantile function. And that's what's represented here. So if you happen to have the inverse CDF of a distribution, it's easy to answer these questions because you just plug in whatever they're asking for. 85th percentile, take your inverse CDF, run 0.85 into it, and the answer is the 85th percentile. It's that one there. So that ends up being a pretty useful stat, which is, that's why people ask for things like median. There's all these problems with asking for the mean because it's affected by outliers, but the median is not affected by outliers. So, that's just the 50th percentile. How do you estimate quantiles? Any questions on what I mean by a quantile? It's just like this generalized median. Okay, so how you estimate these things from sim data is that you have a bunch of replications. So you've done your, it could be replications or it could be customers. You might ask about this about the customers. So you have a bunch of customers. So you got like 1,000 customers and each one of them has a wait time. Sort their wait times. So this is the lowest wait time. This is the highest wait time. And then just figure out what the ranking is that corresponds to that percentile. So if you're asking for the 85th percentile, then just multiply the total number of customers by 85% and take the ceiling of that. So if it comes out that would be, that's 76.5 in the ranking, round up to 77, and whoever your 77th customer is, you take that to be your quantile. So just like a median, your quantiles will actually be a member of your data set. So, and that member of the data set will have 75% or whatever the quantile is of the other data less than it, and then everybody else above it. That's how we estimate quantiles. Questions about that? Okay. So that, like I said, is very useful. So it's used in a lot of designs. So when civil engineers are designing speed limits, a speed limit is actually supposed to represent the 85th percentile speed on that road. So they're not, they're not saying 100%. They're not expecting. They might be requesting, but they're not expecting 100% of drivers to drive less than that speed. If they're successful at setting the speed limits and setting enforcement, then they're expecting that when you look at the data collected for speeds, that 85% of the speeds will be that speed limit or less. And so likewise, you can ask your sim, like if you could build a simulation of an intersection or of a highway, and you could experiment with different things. Like, so you have a driver model that you think is accurately models how humans drive. And you could introduce different infrastructure changes in your simulated world. And you say, without the infrastructure changes, I get a distribution of speeds, which looks like the real distribution of speeds. It's validated. But then I introduce a new speed limit, a new way to enforce traffic, maybe a traffic shaping thing, like all those things in Maple Ash that are death traps that you have to kind of drive around in every intersection. Like in the middle here, you could introduce all of those things and then see how that affects the speed of your simulated cars. And rather than kind of saying what the average speed is, you might come up and, again, what's going to be more interesting to the civil engineers is what's the 85th percentile speed. So you look at the distribution of speeds and you say, out of my sim, the 85th percentile speed, when I don't change it, is what we normally have. Like right now, you wanted it to be 45 and it's like 65. I've done my intervention and now it's back down to 45. So that's an example of how you might use quantiles here. Any questions on that example? So then another way to do that is to, and comes up a lot, is that to generate your own statistics with a simulation as your null generator. Now, what do I mean by that? The idea here, generally speaking, is you notice in real life something that seems like it's probably an anomaly, but you don't have a way to test that. What you really need is a p-value. You need to say something to say, could this have happened in the real system? Under normal situations, under normal circumstances. So is this something that happens more than 5% of the time? Or is it something that happens 5% or less of the time? So you need a p-value on something you observe. So in this case, it might be that, for example, so this is not meant to be topical, but the recent burglary of the Louvre, sort of maybe could motivate this. So the idea that you have an expensive item that has been stolen from a museum, and the item would have taken extra time to remove during the alarm period. A suspect is observed leaving the museum late, but he claims that the confusion just caused him to take a longer route and move at a slower pace. So the police see this person, they're like the last person out of the museum, and they want to say, like, it's really weird. Like, they didn't have the object on them, but it's really weird they're leaving so late. It's suspicious. It's a little sus. So what about this person? What evidence do we have that this person could just be part of, are they in the null distribution? So the blue here is everybody leaving the museum just because they heard the alarm and they're leaving. The red distribution is all of these who might have been doing something else. And so that's the question there. So we don't have a statistical test for this, but what we could do is construct a sim with a distribution of possible speeds and a distribution of possible routes. And so you could imagine that I've got a sim of the museum, the layout of the museum, and I put people in the museum in all the places they normally are, and then I trigger an alarm in my simulation, and then I watch all the different ways that people moving at normal speeds could get out of a museum. And then I get a distribution of times for how long it takes those people to get out of the museum. And then from that distribution, I can evaluate, does this time that was witnessed in real life, is this consistent with the null model that I've built in my sim? And that might look like this. So I built a sim similar to this just to demonstrate this idea. And these were the times that I got out of that sim. And so you see most people got out of the simulated museum in this chunk here. And then there was this long tail that went off this way. And so I can use this as my null distribution for my newly created statistical test. So I can now say, all right, well, the 5% critical value is in my simulated outputs is this dashed line, which means anything from this dashed line or higher, those are times that occur in less than 5% of the outcomes. So if I was asked, does it make sense for someone to be leaving the museum at this time here? That's in the 5% tail. So I would reject the null hypothesis. I would detect that this person is probably not somebody who was just fleeing the museum based on a normal alarm and happened to take a little longer than everyone else. So that's another way that these quantiles are really great, because you can now use sims to generate null distributions, and then you use the quantile estimation to give you critical values that you can use as criteria for classifying whether something is consistent with the null or inconsistent. So the lesson there, the quantile estimation was this critical value. So that's effectively the 95th percentile time it takes to leave, time to escape. Questions about that? Okay. And so as you're even thinking about your final projects, if you're trying to think about like more interesting outputs, more interesting questions to study, you can get out of the thinking just about averages, and maybe you want to think about something like this instead. That's fine. Okay, so we good on that? Those are our point estimators that we care about. arithmetic mean, the time average, and the quantile estimators. Okay. All right, so now we're into the meat of things this unit, interval estimation. So those point estimators, they give us those points at the end of each one of these replications, but you don't ever want to just report a point to a stakeholder. Ideally, you'd like to ask them, what's your null? Like if I were to run my sim and I got a value, then what's the value you would expect to come out of my sim? And if the sim produced a value very far away from that, then it would be surprising. And that's kind of weird to say all of that to a stakeholder. So instead, we don't ask the stakeholder anything, and we give them an interval of hypotheses that a t-test could not reject. That is what a 95% confidence interval is. So the confidence interval here, we have an average value that comes out of our sims. So we ran, let's say, 5 or 10 replications. So now we're at the replication scale. So at the end of every sim is this y sub I over here. That's the actual, say, arithmetic mean of wait times within that sim. And then there are R replications. So this should be an R up here, not an N. So sorry about that. I can go up and fix that. But the idea here is that we say we simulated a Monday, Tuesday, Wednesday, Thursday, Friday. So we have 5 replications. So we are now going to take the average across those 5 replications. And so we had an average within every replication, and now we're taking the average across all those replications so they can report the average wait time for this system. Now, that average is always going to be off. And so the confidence interval helps quantify how far it is off. So we calculate a so-called half width of the confidence interval. So if you see HW in your homeworks, on exams, in the textbook, that's what HW is. It's the half width of the confidence interval. Usually 95%. So if it doesn't say 95%, assume it's a half width of a 95% confidence interval, but it could be a 90% half width, and it'll probably say 90% HW. So the half width, which we learn how to calculate here, which we'll get into that in a second, is just, it's centered on whatever average comes out of that simulation, and then minus the half width and plus the half width. And everything in between, these are the hypothetical values of the thing you're trying to estimate that cannot be rejected at your 5% error rate. So the 95% and 95% confidence interval, that's 1 minus type 1 error. So whatever the type 1 error is, you do the complement of that. So if I have a 10% type 1 error rate, then it'll be a 90% confidence interval. If I have a 99% confidence interval, that's a 1% type 1 error rate. So what the confidence interval summarizes to you, so a 95% confidence interval, is if you pose any of these values inside this interval as a null hypothesis, then it would be unable to be rejected by a t-test at the 5% level. That's what a confidence interval is here. So another way to say that is the probability that the confidence interval contains the true system mean is 95%. So if you run the simulation, so you run your 10 replications, you generate a confidence interval, and you give that to your stakeholder, what you're saying to your stakeholder is, I don't know what the true mean of the system is, but I am 95% confident it's one of these values. So in other words, I'm willing to say that 5% of the time, it will be outside of these values. But 95% of the time, it's one of these values. So if I ran my experiment again, I'm going to get a different confidence interval. But it will likely overlap with the confidence interval that I just generated. And that overlap will likely contain the true mean. And so if you run 100 experiments and generate 100 confidence intervals, 95 of them will include the true mean, and 5 of them will miss it. That's what a confidence interval is. So the usual confidence interval, the half width we use is based on the t-test, two-sided t-test. And the half width here is this formula. And this formula is just the standard error of the mean, which is the standard deviation that you measure or estimate, divided by the square root of the number of replications. scaled by the critical t-value for this many data points minus one. So for that degree of freedom. And I mentioned to you that 1.96 value, which is the critical value on a two-sided normal distribution, on a two-sided z-test. It's the value that corresponds to 97.5%, that quantile of the CDF of a normal distribution. That 1.96, as the number of samples goes to high numbers, and usually when this number of samples, so the number of replications, when the number of replications hits 30 or higher, this is about 1.96. So if somebody tells you the standard error of the mean, if you want to try to figure out what the confidence interval is in your head, then you just double the standard error of the mean, and you get a good ballpark of what that half width is. And we'll see examples of that. Okay, any questions on this general idea that this interval are all of the hypotheses a t-test will fail to reject? Okay, and you can solve for this. Like if you start with your t-test and then just move, be careful about the inequalities and just move things around, you can then solve for the hypothesis, the null hypothesis in the t-test, and you will get this confidence interval formula out. Okay, so if you're given a half width and you're told the number of replications, you can back out things. So you can then back out the estimated standard deviation of the population. So you just work with this formula. So if I know the number of replications, I can look up the critical t-value, I can rescale things, and I can get the standard deviation out. So confidence interval actually compactly summarizes a lot of things. And on top of that, if I know the confidence interval was used, then I know someone assumed normality, because you can't use a t-test unless the data are assumed to be normal. So you can't use this confidence interval unless you assume the data are normal. Well, now I know an estimate of the mean of the distribution. That was the center of the confidence interval. And I know an estimate of the standard deviation. So I can now calculate the quantile here. So I can basically say, well, what would assume that the distribution of my data are normally distributed with the mean from the confidence interval and with the standard deviation estimated with this formula. And now I can use that to calculate an estimate of quantiles as well. So there's a lot of information that comes compactly summarized in a confidence interval. There's also a two-sample version of this, of a two-sample use of the confidence interval. So this is really nice if you say like, what's the average wait time for this simulation? And then someone else generates another sim, and I say, okay, what's the average wait time for that simulation? And at this point, you'd like to compare those two sims. But all you have is a confidence interval for this sim that's written in a report. All you have is a confidence interval for this sim that's written in a report. And so if you have the data, you could do a two-sample t-test. You could take all of the data that came out of this sim, all the data that came out of this sim, put them in a two-sample t-test and say, is there a difference? But you don't. All you have is confidence intervals. But one of the tricks that is true with a confidence interval is if these two confidence intervals from these two systems, maybe my intervention A versus intervention B, so proposed change A, proposed change B, if these confidence intervals do not overlap, then if you did do that two-sample t-test, they would be significantly different. So if somebody gives you confidence intervals and you want to do a pairwise comparison, you just see, do the confidence intervals overlap? If they do overlap, you can't say anything. But if they don't overlap, then it turns out that they can be concluded to be statistically different or significantly different at the 5% level. So if they give you error bars like SEM instead, I already mentioned this, that roughly doubling the error bars is going to give you the half width. So if they say that this is 5 plus or minus 2, and you say, well, what is the plus or minus? Oh, that's my standard error of the mean. Then double it, and the confidence interval is 5 plus or minus 4. And then so now the confidence interval here, maybe the confidence interval here. Now you can compare them. You don't even have to do a real t-test. So I think I've got graphs of that. So like someone can show you an experiment like this one. This happened to be an experiment on enzyme activity, but it doesn't matter. This could be average wait time. and they have a control treatment. You can think of this as your as-is system, a treated system. You can think of this as your proposed system. And they come out of it, and they say the average for the as-is system was this, plus or minus these error bars. And the average for this one was this, plus or minus these error bars. You look up here and you see, oh, their error bars are the standard error of the mean. So to get your confidence interval, you just visually double that. You say, well, if I take this and add the same amount onto the top, and then I take this width and add the same amount to the bottom, then I see that these two confidence intervals, unfortunately, they intersect. And so it doesn't tell me anything about this population, and I have to then run a true two-sample t-test. But if they didn't give me error bars, if these were instead confidence intervals that were plotted, well, these do not intersect. So if the confidence intervals did not intersect, then just looking at this graph without even asking for a p-value, then I would know that the treatment or the proposed system has a significantly lower value of the response variable that I care about. So questions about that, this idea there that you can go from standard error to confidence interval, and then when you have confidence intervals, you can compare confidence intervals. You can only do this with two populations. Once you go to 3, 4, or 5, you've got to use more sophisticated methods like ANOVAs and things like that. But once you have just two, if you get two confidence intervals, it's totally legal to compare those. And if they don't overlap, you don't have to do a t-test because you know what the answer will be. Okay. All right, so let's do one of these then, following that example. The short answer, I guess. All right, question here. Let's say you're given a plot that looks like this one, and you're told that these bars here represent 90% confidence intervals. So if these are 90% confidence intervals and they do not overlap, so there is daylight in between them, you can take a sheet of paper and stick them so that you can't. It's like it's like a middle school dance. You can separate them out. So then, if you can separate these two things out, they're not touching, and they're a 90% confidence interval. What can you conclude about the p-value of a two-sample t-test that would hypothetically be done with these data? If you had these data and put them in a two-sample t-test, what p-value would you get out? So you don't have to actually do the test. You can actually tell something about these p-values. So what can you conclude about the p-value of a two-sample test if you know these non-overlapping confidence intervals are 90% confidence intervals? So as a hint, what I'm looking for is that the p-value is less than or greater than a particular value. So that's what I'm kind of looking for here. So there's two aspects of this. Is it p-value less than or p-value greater than? And what is the threshold that we're corresponding to? So if those are 90% CIs, what is the threshold? And is the p-value less than or greater than the threshold? So go ahead and scribble your answer in. I'll give you another 5 seconds, maybe. Or maybe 3 more seconds. And I'm about to hit close, closing right now. All right, so what's the answer? How many people, okay, I'll do this. How many people said that the inequality should be less than? How many people said greater than? Okay, how many people then said that the threshold so it was less than, that's what I was looking for, P is less than, and now the threshold. How many people said the threshold was 5%? What about 10%? Okay, what about 15%? Right, so 10% is what I was looking for. So if somebody presents to you a 90% confidence interval, then you know that that corresponds to a 10% type 1 error. So if we've concluded that they are significantly different at the 90% confidence level, we are saying that we will say they're different with a 10% type 1 error. Okay, great. All right, so confidence intervals. Given that I already kind of mentioned this already, given that you're given a confidence interval, you can estimate distribution and quantiles. So this is just writing out a math that I said just a few minutes ago, where if you know the mean from a confidence interval, that's the center of the confidence interval. That's all this is saying, is that from the lower and the upper bound divided by 2, the center of the confidence interval is the mean. And if you know the half-width of the confidence interval, that's just the range of the confidence interval divided by 2, you can solve for the standard deviation of corresponding to that confidence interval. Because the confidence interval is the embodiment of a t-test, it means whoever calculated it assumed that the data were normally distributed. So then I can say, all right, well, if I assume if under the normality assumption, I'm just going to assume a normal distribution with this mean and with this standard deviation. So if I just take a standard normal and I compare it to a z-score based off of whatever. So if I want the CDF for my data is just going to be the z-score for that CDF, where I use this mean and this standard deviation. And then I compare that z-score to the CDF for a standard normal. And that will give me the exact same thing, or give me a very good estimate of the CDF of my data set. So with that, I can then calculate quantiles. So I've got, I can calculate a quantile here. So if I know the critical, so this ZP, that's the critical Z value from a Z-test table. And so from there, I can figure out that, okay, so if you're asking for a 95th percentile, well, I can figure out what Z that corresponds to, scale that by my standard deviation, add my mean, and then that will give me the quantile for my distribution. So if you're given a confidence interval, you're given a lot of information. You can back out a lot of information, because not only are you given the confidence interval, you're given the assumption that the data are normally distributed. Okay, questions about that? It's a minor thing. I'm actually probably not going to ask you to do this, but I do ask you to back out other information from a confidence interval. I will ask you to do things like, here's a 95% confidence interval, give me the 90% confidence interval. So that's very similar to this. Okay, so last kind of interval idea is, I mentioned quantile estimators. That's another point estimator. We can't ever trust point estimators. And so this is a little bit hard to process because of all of the percents that are involved, but you can generate a confidence interval on quantiles. So you can say, this is my 95% confidence interval on the 95th quantile. So, which is a little bit of a mouthful, but hopefully it makes sense, this idea that you run your sim and you end up getting, you say, somebody asks for what's the 85th percentile speed? And you can say, well, it's 45 miles per hour, or it's 46 miles per hour, something like that. And then they say, well, how confident are you that it's 46 miles per hour? Like, it's in a range, right? So is it from 0 to 90, or is it from like 44 to 48? So that's what they're sort of asking for there. So you'd say, what is the 95% confidence interval on the 85th percentile speed? And so that's what we want to be able to generate. And you can do that with some light assumptions. So these are the sort of standard assumptions. We can calculate a half-width for percentiles that, interestingly enough, only depends upon the percentile you're asking for and the number of replications. So for this case, because there's certain assumptions that I'm not going into, we don't actually care about the standard deviation of the estimate. So if you're asked for a 75% confidence interval, then you put in your, if you're asked for the 75th quantile, the 75th percentile, then you put in your 0.75 in for P. If you ran 100 replications, you put in 100 in for R. And if you're asked for the 95% confidence interval, you put in 5% for alpha. And with that, you get a half-width. But a half-width of what? It's a half-width of of quantiles, basically. So it's like if you're asked for the 0.85 quantile, it's going to tell you in your ranking, you're going to want to go back not only to 0.85, you want to go all the way back to 0.81, and you want to go all the way forward to 0.89, for example. And I'll show you an example on the next slide. But so we have this calf width. And so the idea here, and here's the example, is that I've got a sim that has these data that came out. So you can imagine each one of these rows are a different discrete data point. So different customer, for example. And I want to then, or a different replication. And so the idea here is that the mean that came out of that is 212.03. Sorry, not the mean, but the point estimate of this quantile is this middle one here, 212.03. So the point estimate of the 80th percentile, or the 0.8 quantile, is just basically 80% in the ranking of the data. And that gets me right here. So now I calculate this half width. And so, and there's the 1.96. It's going to show up over and over again. For a 95% confidence interval, the Z value that comes out of that critical Z table is going to be, for a two-sided test, is going to be 1.96. So this is my half width here. So 1.96 square root. There's the 80% in the numerator. There's my 1,000 data points in the denominator. And that says that my half width brings me down to the 78th percent ranking and up to the 82nd percent ranking. So how do I calculate the confidence interval here? Well, I go to the 78th percent of my ranking, which brings me all the way down to this 188.96. And I go up to the 82nd percentage spot in the ranking. So when they ask for the 95% confidence interval for the 80th percentile, then I give them this interval here, which is just saying to them, I don't know the exact answer, but I cannot reject anything in this interval. Outside of this interval, I can reject. So if they were to ask, like, what is your 80th percentile? I'd say, well, it's not 150. I'm going to reject that. And it's not 275. I'm going to reject that. Is it 190, 195, 250? I don't know. I can't tell the difference between those with the number of data that I have. But I can tell you it's not outside the confidence interval. That's why, we talk about polling results this time of year. They talk about margins of error. What they're really saying is if you're estimating the fraction of people, which is definitely related to this, if you're estimating the fraction of people who voted for a particular thing, if that fraction includes 50%, then that means we have no idea where the majority lies. But if that fraction excludes 50%, then that means that we have no idea exactly how many people support X or support Y, but we know that it is a majority. So it might be 60%, it might be 65%, it might be 70%. It's somewhere in there. All of those are greater than 50. So we've rejected the hypothesis of 50%. It is a decisive outcome, even though we don't know exactly how many people support that. That's the idea here too. Questions about that? Okay, and they do use, they use a little more sophisticated methods, but when they are calculating those confidence intervals on those percent supports, they are using a formula that is related to, or once upon a time, they were using this formula. There are, again, more sophisticated ways to calculate confidence intervals on percentages now, but still, that's a good place to start. And so that's usually where I tell students to start, is that one. Okay, so any questions about any of that? Interval estimates. So that's our big thing. From here on out, from this point on in the class, no more point estimates. When you give on your final project report, then you are going to be, there. So then on your final project report, I don't want to see our average wait time was 6 minutes. That doesn't mean anything, because if I reran your sim and it came out to be 1 minute, and then I reran your sim and it came out to be 15 minutes, then I don't care that your sim ran and it was 6 minutes for that one. Like, that's a huge spread. So you need you to capture that spread. So I need you to say, instead of the average wait time is 6 minutes, You can, if you want to use plus minus, you can say the average wait time was 6 minutes plus or minus, 1 minute, and then make it clear that that 1 minute is a half width. Or you can say the average wait time had the confidence interval of 5 minutes to 7 minutes. And then that gives me an idea of spread. That tells me that, oh, I get it, that you have some error in your estimate. And so the error in your estimate is captured by that 5 to 7. So that way I can't make any conclusions within 5 to 7, but I at least know it's not 4 and it's not 8. So interval estimates from here on out. All right, and so I'm going to skip this arena stuff. So basically just it talks about, and you'll go over this in lab, but there's ways to get discrete data and time persistent data out of arena. So again, you'll play with this in your lab. The confidence interval results are reported inside arena. And so you can pull those right off of there. There's, if you, these DAT output files can be loaded into the output analyzer. That will be a big part of lab 9. And then that output analyzer helps you calculate confidence intervals that we just talked about. So that'll be something, again, you'll do in lab 9. And then it'll even allow you to do more sophisticated analyses. So you can compare means, and there, a paired t-test or 2-sample t-test. So you can do the t-test right inside this arena tool. If you have more than 2 groups, you can do an ANOVA right inside this tool. Notice that they have Bonferroni correction that's built right into it. So you can adjust the confidence levels yourself, or you can have it do it for you. So all these things we've talked about are loaded somewhere into this tool. So it's good to recognize these terms because you're going to land on tools like this. And then they have all these options. Where do these options come from? They come from the issues that we've talked about here in the lecture. So that'll be stuff that you'll play with in lab 9. Then in lab 10, you get to look at the process analyzer, which is even nicer in that it runs all the experiments for you and it effectively sets up the data analysis for you. So then you just need to interpret. So in lab 10, in the process analyzer, you can basically say, I built a model. It has variables in it. I want you to swing the variables from a low value to a high value. And do basically run all of these experiments. I want you to run them a certain number of replications each, and then I want you to take all the data that's out and summarize it like this. And so these summaries allow you to say, okay, scenario 1, this the blue and red here have to do with what things you can tell apart, like which confidence intervals don't overlap and which ones do. So when it does something like this, if you say, I'm interested in the highest value, what it's telling you here is that I can't tell the difference between scenario 3, the numbers you had me put into, like, this is like proposed intervention 1, proposed intervention 2, proposed intervention 3. And it's saying these 2 interventions, their outputs are so close, I can't tell the difference. They like have overlapping confidence intervals. But this one is so far above these that this one I can tell is significantly different from both of the other 2. So even though I can't tell these apart, I can tell that this one is significantly greater than this one with statistical significance. So it does all that stuff for you. And then you just have to look for the colors, basically. You run the thing and you say, if I'm looking for maximums, then I pick scenario 1. If I'm looking for minimums, I pick either scenario 2 or 3 because they are statistically equivalent, even though there might be some slight difference. I didn't run a large enough experiment to be able to tell them apart. Even if I could tell them apart, they're not going to be that far apart. So that's what we get out of the process analyzer, which you're going to use in lab 10. And then you can go even farther in lab 10, where you can actually tell it to do the optimization for you. So you can say, hey, Arena, here's a model. Here's all of the decision variables I could change. Find me the best set of decision variables. And it will automate all of that for you. And it just then pops out to say, you should have this many cashiers, this many lanes, and so on and so forth. And then it'll give you a summary of what the data look like for one of those things, but it automatically iterates around that. It doesn't run everything it possibly could. It runs one probe, and then based on the result from that probe, it then moves the decision variables and runs another, and it moves the result, runs another. And after it does that whole thing, it settles out, and then it makes a conclusion, and then it gives you that conclusion and says, this is what I think is optimum for your system. So that's what you're going to see in lab 9 and lab 10. All right, so we have a little bit more to talk about today, which is about setting the number of replications on transient sims. It's not much. The steady state sims will be the bigger discussion for next time. So before we do that, any questions about any of this interval stuff behind me? Okay. All right. So let's knock this out then. So transient sims for terminating systems. This, because we include all of the data, we don't have many decisions to make. Once we've built the model, we want to keep all of the data so we don't have to decide how long to run the sim. That's fixed. The sim only runs this long. We don't have to figure out how much data to throw out. We don't throw out any data because it's a transient sim. We care about all of the data. The only thing that we have to decide is how many replications to run. And so how do we do that? Well, all the stuff we've learned about power analyses and these confidence intervals gives us enough to make this decision. So that's why this is here. So this is, example of the data. So we've got our replications and then a certain number of outputs per replication. So within the replication, you've got this many customers. So then across that replication, you've got a mean for the customers, a standard deviation or a variance for the customers, and a half-width for those customers. Now, we're probably not going to use that half-width because these customers are probably not independent. So it probably doesn't make sense to use a half-width when you talk about within replication data. But then you have across replication data. So then for each one of these replications, you can take each one of these means, and then you've got a mean across the replication, a variance across the replication, and a half-width across the replications. And these are the ones we usually care about more. We treat these as per replication outputs, really. And then the stats are run on these. So our stats are an average of averages. The first average is not a statistically meaningful average. It's just a summary of the replication. The second average is a statistically meaningful estimate. That's the idea there. So across replications, down, within replications, left and right. And we can do that both with discrete data and with continuous data. So that's all that we're saying here. All right, so summary of stuff I've just talked about there. Across replications, we definitely can do a mean. We definitely can do a variance. Whether we can do a half-width, whether we're allowed to calculate a half-width, depends on whether the across replication data meet the assumptions of a t-test. The half-widths we use in this class are based on a t-test, as most half-widths are. There are half-widths based on other tests, but it gets a little deeper. And so if you can say all of your replications are independent, which you should be able to because your random number generator ensures that, and you can say they're normally distributed, then you're allowed to calculate a half-width based on those data. But if they're not normally distributed, then the best you can do is a standard error of the mean, this portion here. You can't scale it by that. But in this class, almost always, it's legal to calculate half-widths across replication. Within replication, we don't have really any assumptions, so we're almost never going to calculate half-widths from within replication data. It just doesn't make sense to do unless we're talking about steady state simulations and we're talking about batching things up. When one batch is very far away from another batch, then we can treat them as independent. But generally within replications, we just have data that are probably correlated with each other. So we can't do half-widths, but we can do means. We can say the average wait time for the 100 customers today, that's totally fine. We can summarize the variance. So the variance in customers today, that's totally fine. And we can do that in the time persistent versions, the continuous versions as well. That's fine. So that's just emphasizing things I said before. Half-width lives across replications, does not live within replications. Okay, so how do we ensure independence across replications? Random number seeds. So I was just saying about that. How do we ensure normality? For this class, you usually just can assume it. We usually want to test it, but in sims, very often the central limit theorem helps us. Because in sims, very often the data you get at the end of a sim is the sum of a bunch of other data. And often enough, those data are independent enough to give us bell curves at the end of our sims. And so normality is usually held. Not always, but usually held. There are variance assumptions that we're going to have to deal with, and we're going to talk about that next unit. But for now, it's usually safe to assume normality, cross replications, but not within replications. So how will we decide the number of replications? Well, if these things are true, then we think about your second question of your homework. We do a power analysis. So the classical way to figure out how many replications I need to run in that sim is I run a pilot study. So I just say, I'm going to run 5 replications of my sim. And I'm going to see what's the average wait time for each one of those 5 replications. And it's going to have some variance in it. And I'm going to estimate the standard deviation of those 5 replications. And that tells me how variable my sim is. From that estimate of variability, then I can calculate an effect size, just like you did in your homework. I can choose a statistical power. I can apply a power analysis, and that'll tell me that based on this power analysis, to get this power, you need 15 replications. We already ran 10, so I just run 5 more. And then from that, then I can use those 15 data points, and then hopefully I've achieved my what my power analysis says that I need. So that's the classical way to do it. Exactly what you did on your homework, just with this pilot run to estimate variance. The alternative, based on what we just talked about today, is to use the confidence interval formula. This does not guarantee statistical power, though, but it's often good enough for stakeholders to say, what is if a stakeholder knows what a confidence interval is, you can ask them, how tight do you want the confidence intervals on this? And they might say, you're estimating a wait time. I want your estimate to be, I want the intervals you give me to be no larger than 2 minutes. So I want a 1 minute half width. So, okay, I'm going to choose enough replications to give you a 1 minute half width on my estimate. That does not say 80%. We have no idea what the statistical power is on that. But we know that it's really a constraint on type 1 error. It's how many things can we exclude from consideration. And so if they tell you they want a half width that's 1 minute, well, we can back out how many replications we need to make that happen. And we use you just solve for R, and this is the half width formula, but solve for R. It's a little annoying to have to use the t-value because the t-value also depends on the number of replications. So let's just assume we have enough replications and we can approximate a t-value by a z. So then we just look in the z table instead of the t table, and then this thing doesn't even depend on the number of replications. So if we know we ran our pilot experiment, we know our standard deviation from our sim, we scale it by the critical z value right here, and then we divide by this half width that our stakeholder wants, this 1 minute that's over here. And then that tells us how many replications we need. And then we just choose that many more reps. That's the idea. So there are 2 methods. Power analysis if you can, use the half widths if you can't. So, and of course, the more replications, the more compute time. All right, I don't want to keep you any longer than that. If you have any questions, feel free to come up. And since we've already done 2 of these, then that's all. So I'll see you. Hope you guys have a nice holiday break. We'll see you in a week.